Every driver knows the strain and the nerve-wracking delays of driving on overcrowded roads. An everyday nuisance, but it is a nuisance that all too frequently has a tragic outcome. The number of cars on the road is increasing all over the world, and the number of road accidents rises with it. To give only one example, traffic accidents in the Federal Republic of Germany rose from over 445,000 in 1953 to over 983,000 in 1961. The numbers of dead and injured rose accordingly. In 1961, more than 13,000 were killed and more than 300,000 injured on West German roads. Statistics published by Cornell University, USA, give the following analysis of road accidents. The impact is frontal in 66% of all city limit accidents and 54% of all accidents on overland routes. On the side of the car, in 24% of all city limit accidents and 14% of all accidents on overland routes. On the roof, in 3% of all city limit accidents and 24% of all accidents on overland routes. On the rear of the car, in 1% of all city limit accidents and 3% of all accidents on overland routes. The chief aim is to reduce the risk of injury in case of an accident. You will see how precautional constructive measures are tested by Daimler-Benz. This rocket gives the test car a speed of 65 miles an hour. It is driven hydraulically. Before release, an excess pressure of 55 atmospheres is developed. The dummy driver is modeled on the human body. Instruments in the head and chest measure the force with which the body is flung against the interior fittings at the moment of impact. These figures are recorded for future reference. Two other instruments between the front seats also record the force of the impact. On the rear wheels, a speedometer. The test car is connected by cable to the control car. The last preparations. The rocket is ready to go.
Starte. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Speed, 65 miles an hour. In car construction, it is of paramount importance to give the greatest rigidity to that part of the car in which the passengers sit. The front and rear are less rigidly built. They should yield. They should cushion the impact. They should absorb the force of the crash. You see the effect. The front of the car is heavily buckled, but even the door frames retain their shape, although no doors are fitted. The other side of the car. The doors can be opened and closed. The locks are undamaged. Not all cars have the same locks. This special safety lock is patented by Daimler-Benz. Locking ring on the door support. The door itself, locking pin and mechanism. When the door is closed, the locking pin is completely secured, held firm by bolts, and is immovable in any direction. Tests with strains of 1,000 pounds and more show that the lock still functions perfectly. Steel barrier, speed 60 miles an hour. The car hits the barrier at an angle of 15 degrees, glances off and drives on parallel to the barrier. The forward motion of the car is only slightly impeded. Here we see buckling at the front of the car. The doors remain closed and can be normally opened. The driver was flung against the steering wheel and door, then on the floor into the leg room in front. Here is a test of rigidity, especially of the roof supports. Speed, 50 miles an hour. The car turns over, landing on its back and roof. Special constructional measures ensure that the rigidity of the body is not affected by the large size of the windows. This is especially noticeable with the coupe, in which there are no center supports. In spite of this, the windows can be opened and shut without difficulty. After the coupe, here is the same test with the saloon. The interior of the car remains undamaged. The doors can be opened and shut without difficulty. A third turnover test, speedometer reading 65 miles an hour. This slow motion picture clearly shows the strain to which the edge of the roof and the front window supports are subjected at the moment of impact. Here too, the doors remain closed. A 50-mile-an-hour crash into the rear of another car. The removal of the doors enables the dummies to be filmed, but the danger of crumpling of the door frames is increased. Nevertheless, no damage has been done. The windows are torn out of their frames. The boot and front of the cars are heavily buckled. The fast-moving car is slowed down over a considerable distance. Here we clearly see the process by which kinetic energy is transformed and absorbed by the yielding metal. Both drivers are wearing safety belts. Here we see the frame floor of the car, and here the subframe is mounted. This construction should also buckle to absorb the impact. Here we see the same parts of the damaged car. Since 1951, Daimler-Benz holds the patent of the construction principle, whereby the rigidity of the interior diminishes towards the front and the rear. Measurements taken on the catapult seat show the pressures exerted on the driver and his companion at the moment of impact. All tests are carried out at a speed of 25 miles an hour. Test 1. Driver with safety belt. No impact. Test 2. Driver without safety belt. He is flung forwards against the padded steering wheel boss. The force of the impact is thus spread over a wide area of his chest. The wheel itself yields to the impact. Test 3. Passenger with safety belt. No impact against the dashboard. The padded lower edge lessens the danger of injury to the knees. Test 4. Passenger without belt. The heavy buckling of the dashboard avoids any serious injury. A similar test with a living subject. Passenger with belt. Speed 12 miles an hour. This cross-section of the dashboard shows the measures taken to absorb the force of the impact. The upper and lower edges are padded. Underneath is deep-drawing metal, which absorbs shock without causing major injury. These properties are checked by a strike test. The ball strikes at a velocity of 40 miles an hour. The construction of the dashboard, however, is only a part of the measures taken to ensure interior safety. Mercedes-Benz cars contain no sharp edges, no projecting parts. If their function requires such parts to project, they are constructed to be flexible, shock-absorbing, or they are recessed. All these measures are designed with only one purpose: to prevent or to reduce accident injury. And now, the testing grounds in Unterturkheim. The aim is to achieve the highest possible safety in driving and to eliminate, as far as possible, the danger of accidents. Brakes are tested again and again. The aims are as follows: effective braking in the shortest possible distance, no jamming by sudden braking, no breakaway of the car, no fading, even after continual sudden braking. Similarly with steady braking on mountain roads. Reliable brakes are often the best security against accidents. Chassis tests on bad roads, including the worst possible conditions. Even on such a surface, a car should hold the road and the suspension ensure driving comfort. Bumps should be as far as possible absorbed by the suspension system. Here is the Mercedes-Benz technical solution of this problem. Front axle with independent suspension, torsion bar stabilizer, shock absorbers positioned close to the wheels, rubber mounting of many parts. The rear axle is a single-joint, low-pivot swing axle. This construction gives good driving control and road adhesion even on bad surfaces. Here we also have shock absorbers positioned close to the wheels and rubber mounting of all shock-sensitive parts. An elaborate and far beyond average construction which ensures highest driving performance, maximum road holding with no sacrifice of comfortable suspension. In addition, a precise, easy-to-operate, recirculating ball-type steering. Constructional security, which facilitates complete control of the car and ensures comfortable driving, the interior being as far as possible isolated against all shocks. Cornering, the biggest source of danger to any driver, especially on wet roads. When cornering, the car should hold the road, behave normally, and allow accurate, easy steering. The more these qualities are developed, the greater is the security of the car and its occupants. Even the average driver should be safe on any curves, on any road surface. No oversteering or understeering on curves. The car's behavior is neutral, thanks to the stabilizing, compensating spring over the axle. One other aim: the car should respond to abrupt steering changes without swaying. even at high speeds. Here is the snaking test. Speed 80 miles an hour. No cost is spared. No new development left untried. You see the advantages. Reserves of security, which can be decisive in many a dangerous situation. Cars with real built-in security. Even so, it is still the duty of the driver to drive well and carefully. Such cars, good as they are, can never compensate 100% for unsatisfactory roads and difficult traffic conditions. But as long as accidents happen, these cars will remain the most vital contribution that the car industry can make in support of the one overriding principle: safety on the roads.